Hello, physics enthusiasts. Approximately Constant here, and today I'll solve the second question from the Physics Olympiad 2023. Let's begin. So, this question is called Effective Equation of Motion. Here, let's read the question together. Results so far imply that particle velocities v of t and v of t prime may be regarded as uncorrelated random quantities if the difference between t and t prime is much greater than tau. On this basis, we introduce a theoretical model to approximately describe the one-dimensional Brownian motion where the velocity changes randomly at each time interval delta. So here the velocity changes randomly with each time interval delta. We're given v of t is equal to vn, where tn is a random quantity and Tn is equal to n times delta. It satisfies the expectation value of Vn is equal to 0 and the expectation value of Vm is equal to 0. Here, is 0 when n is not equal to m and c when n is equal to m. Here, this angle bracket are called the expectation value and they're similar to the mean. So the properties of the mean will um, can be applied to expectation values. Now we consider the particle displacement this for t is equal to n delta with an integer. The first question is determine delta x, the expectation value of delta x and delta x square using c, delta, and tau. So let's get right to it and solve the question. So what we're given is we're given v of t is equal to vn. Um, and the mean value of Vn is equal to 0 and the mean value of Vm is equal to c times the Kronecker delta function. This Kronecker delta function is just a convenient way to write it down. This function is equal to 0 when n is not equal to m and 1 when n is equal to m. Also, Tn is equal to n delta. The question says find delta x and delta x square. Now, first to understand this question, let's plot what the diagram for v of t and t should be. It should look something like this. First, their time is split into time intervals delta, 2 delta, 3 delta, 4 delta, 5 delta. And for each delta, we choose a random value for v. For the time between 0 and delta, the value of v is v1. For delta and 2 delta, it's v2. And similarly for v3, v4, v5 up to vn. And the mean value of v is equal to 0. So this is somehow what the graph should look like. Let's try to solve this question. We know that delta x of t is equal to the integral from 0 to t of v of t dt. This integral from 0 to t can be split into 0 to delta, delta to 2 delta, 2 delta to 3 delta. So we write 0 to delta, delta to 2, 0 to delta, delta to 2 delta, and so on. Now, when the time is between 0 and delta, v is equal to v1. Similarly, when time is between delta and 2 delta, v is equal to v2, and so on. Now, this integral is nothing but the final value minus initial value, which is delta minus 0, which is delta. Similarly, here we'll get 2 delta minus delta as delta. Here n minus 1 delta, n delta minus n minus 1 delta, so delta. So what we get is delta times vi, sum from I is equal to 1 to n. Now, if we take the expectation value on both sides, we get the required expectation value is equal to this. Here, delta is a constant, so it'll come out of the expectation value and we'll get one I goes from 1 to n, the expectation value of v. The mean value of v is 0, so this should be 0. And every something multiplied with 0 is 0, so the answer to this is 0. Next, we have to find the expectation value of delta x squared. So for that, let's calculate delta x squared. Now, delta x squared is nothing but summation vi delta squared, which we can obtain as delta squared times vi vj. Now, taking expectation value on both sides, like we did previously, we get this expression. In this expression, we're given that this is equal to C Kronecker delta ij, and when we sum this over all j, we get 1, and summation of this summation is equal to n. So finally, we get this. Now we are also given that uh, t is equal to n times delta. So n is equal to t by delta. Using this relation and the quantity derived above, we can write this to be delta squared c t by delta, which is equal to delta ct. Now let's look at the second part of the question. The second part of the question is states that this delta, the expectation value of delta x is called the mean square displacement. It is a characteristic observable of Brownian motion, which corresponds to the limiting case delta goes to 0. From this, we can show that c is proportional to delta raised to the power alpha, and x is equal to, I mean, mean square displacement is equal to is proportional to t raised to the power beta, and we have to determine the values of alpha and beta. This conceptually is a little bit difficult, but let's think about it. So we are given that this limit, when as delta goes to 0 of the mean square displacement, is a characteristic of Brownian motion, which means this limit exists and it should not equal 0. So we're given that this limit is equal to some number other than 0, and we have to find alpha and beta which satisfy c is proportional to delta raised to the power alpha, and the mean square displacement is proportional to t raised to the power beta. So we can solve this question easily if we take if we substitute the value we got from earlier. T does not depend on delta, so t will come out and we'll get limit delta goes to 0 delta c, which is only non-zero when this limit exists, and is non-zero only when c is inversely proportional to delta. So alpha is equal to -1. Similarly, uh, the mean square displacement is proportional to t, so beta is equal to 1. So this is the final solution to the question. I hope you guys enjoyed the video, and I'll see you next time.